So we'll be looking now at the issue of estimation of transition intensities in multiple state models. We discussed state models before. You understand multiple state models before, and you understand them. We'll start with the context of the simplest sickness-death model in disability income insurance. You're familiar with it. We talked about it before. Very simple, with one complication, that there's a state of healthy, 0, sick, 1, and dead, 2. And the state of being dead is absorbing, as always. However, you can move from state 0 to state 1 and back over and over, so you remember that that is a complication. That means that we may have to use a Kolmogorov-Forward equation for finding out probabilities, what the probabilities are. We will work with this model to discuss this topic. To estimate transition intensities for models with multiple states, we consider each age separately, and we assume that all transition intensities are constant within each age year. So between age x and x plus 1, the force of transition for each possible transition is constant, and then it may change next year. So this is a bit similar to the constant force of mortality in the year of death assumption that you have seen in Mathematics 380 or some other context of studying life contingencies before. We construct a likelihood function using the observed data for each life, consisting of the time spent in each state, the number of transitions between states during the age year. And remember how you construct the likelihood function. You take the probability density function, evaluate it at the data points that you have. You assume that you know what the probability density function or the probability function is. So you're working with a certain family of probability distributions with a certain formula with parameters in it. You plug in the data and you take those values of the PDF probability density function at multiple points. You multiply them out for various points, data points. You get a whole expression for likelihood, and then you maximize it to obtain the values of the parameters estimated. You've learned two main methods of statistical estimation in basic mathematical statistics class. One is the method of moments, where you match the empirical distribution, so the data points, moments, like the mean and the expected value of x squared, expected value of x cubed, where x is the random variable, and you match this to the expected value e of x squared, e of x cubed, from the theoretical distribution, and whatever provides the best match, that's the value of the parameter that you use. So we're using the maximum likelihood estimation now. Recall the difference between type 1 and type 2 right censoring. That's one more issue for us here. The data that we're working with is censored. That means that we don't get to observe all of it. It's limited in some way from our observations. Type 1 is where completely random dropout, for example, immigration, and our fixed time of end of study with no event having occurred happens. So the study is just cut off in some way. And then type 2, study ends with when a fixed number of events amongst the subject has occurred. So it's also cut off, but it's cut off differently because we cut it off when we get enough data for whatever our purpose is. If the life under consideration stayed in the same state throughout the observation period or until a fixed type 1 censoring point, then the contribution of the likelihood is the ex ante, so ex ante before the event, probability of staying in that state. If the life moves between states, then the contribution of the likelihood is the joint ex ante probability function of the observed movements. We use, and ex ante refers to the situation that we have before the estimation. We assume a certain model. Okay? We use the term probability function to cover both cases. Suppose we observe the following history for a life between ages x and x plus 1. At time 0, a person is age x and is in state 0. Time point 1, at hx plus 0.1, transition to state 1. At time point 5, at hx plus 0.5, transition to state 0. At time point 8, at hx plus 0.8, transition to state 2. To state 1, not state 2, not dead, 1. At time 1, at hx plus 1, still in state 1. We partition the entire interval between ages x and x plus 1 into subintervals based on the events listed. The first interval of values of t is 0 to 0.1. The likelihood contribution is, well, the probability density function of staying continuous as applied to staying continuously in that state, which is 0.1 px00 bar. So you stay there, and then you get taken out, but you get taken out by transition to state 1. What is the probability of that? So the PDF of this staying there is what you see here. This is multiplied by mu01 plus mu02. And that's the form of the PDF for life contingencies. It's always probability of staying there and then getting whacked by the force. But then you get whacked by mu01, and what's the probability that you get taken out by this instead of a mu02? And that's 2 exponentials time of first arrival. I gave you some notes about this earlier in the class. And the probability of that is the intensity of the thing that takes you out versus divided by the sum of the 2 intensities. So, but that's simply 0.1 px00 bar times mu x01, which is very intuitive. It's you stay in that state 0 and then you get whacked by a force taking you from 0 to 1. The second interval is 0.1, 0.5 with likelihood contribution of 0.4 px11 bar. There's a bar above it there, you see, times mu x10. The third interval is 0.5, 0.8 with likelihood contribution of 0.3, because it's the length of the interval is 0.3, px00 bar times mu x01. And the fourth interval is 0.81 with no transition at the end, but censoring end of observation, and the likelihood contribution is 0.2 px11 bar. And you multiply those out, and this is the likelihood function. But the intensities are constant, so the tpx00 bar is e to the minus t times the sum of the forces trying to take you out of state 0, and tpx11 bar is e to the minus t times the sum of the forces trying to take you from state 1. And though you plug it in, you get this likelihood function, and it's simplified nicely. The precise timing of the transitions doesn't matter because this is constant intensity, so like exponential distribution, doesn't matter how old you are. The probability of death does not depend on age. So it's a consequence of constant transition intensities assumption. And the only information required is the time considered spent, the life considered, the person whom we consider is spent 0.4 years in state 0, and we will denote that time spent in state 0 by t0 in brackets. The life considered spent 0.6 years in state 1, and we will denote time spent in state 1 by t1 in brackets. The number of transitions from state 0 to state 1 was 2, and we will denote that number of transitions by d01. And the number of transitions from state 1 to state 0 was 1, and we will denote that number of transitions by d10. And finally, there were no other transitions during the year. For a more general formula for the contribution of the likelihood of a single policy history, assuming the sickness-death model with piecewise constant transition intensities, we adopt the following notation where we consider all events occurring between ages x and x plus 1. Tjk denotes the total time spent by the jth life in state k between ages x and x plus 1. This is also called the waiting time in state k for the jth life. And of course, you know that from the consideration of Poisson processes at the beginning of the class, where you had the waiting time until the claim occurred. This is a similar concept. And djik denotes the total number of direct transitions by the jth life from state I to state k between ages x and x plus 1, with I not equal to k. Then and direct transitions, because you can also go through other states, but no, this is going from this one to that one. That's it. Then with state 0, 1, 2, and state 2, absorbing, which is the sickness-death model we have, the contribution to the likelihood for the jth life is of this form, that it's e to the minus tj 0 times mu x01 plus mu x02 times e to the minus tj1 times mu x10 plus mu x12 times mu x01 dj01 to the power dj01 mu x02 to the power dj02 times mu x10 to the power dj10 times mu x12 times dj12. Note that we added now possibility of death, and those are included, but we don't add any possibility of staying in a dead state and then returning to some other state, which is the first two terms refer to staying in some state for a while and then going somewhere else. Of course, a state of being dead is absorbing. So an example here, an insurer is analyzing the experience using the sickness-death model. You are given the following records of all transitions between ages x and x plus 1 for 3 lives. For each life, identify the values of t0, t1, d01, d02, and d12, and write down the, well, I guess we could possibly have d10 as well, and write down the contribution to the likelihood function in terms of the transition intensities. So this is what you have. Life 1 is in state 0 throughout the period. Life 2 is in state 1, then moves to state 0, then moves to state 1, and at time point 8 moves to state 2 from state 1. Life 3 is in state 0 at the beginning, moves to state 1 at time point 4, moves to state 0 at time point 5, well, sorry, point 6, and moves to state 1 at time point 9, and is in state 1 at the end. So we have life 1 is for the whole period in state 0, so t0 is 1. Life 2 spends point 2 in state 0, point 6 in state 1. Moves once from 0, 1, moves, doesn't move from 0 to 2, moves once from 1, 0, so that should have been there in the description of the exercise, and moves once from 1, 2. Life 3 spends 0.7 in state 0, 0.3 in state 1, moves twice from 0 to 1, never moves from 0 to 2, moves once from 1 to 0, and never from 1 to 2. Then trying to think. Oh yeah, okay. Life. It's not life 3 that dies, it's life 2. Of course, yes. Then the contribution to the likelihood function, the contributions are, as you can see here, and all of this is a function of the forces, right? We can collect together the contribution to the likelihood from, say, n lives under observation between ages x and x plus 1 to give the full likelihood function, and it's a product of everything. So this is the general case like that, with not just 3 lives, but n lives. And the log likelihood function, well, why do we have log likelihood? Because the likelihood function, as it is stated here, is complicated. It has exponential function, it has powers, and so on. How do you simplify this to find the maximum? Well, you could take the derivative and struggle with this like crazy. Or you can recall that you learned that when you were solving equations that involved powers and exponentials and so on, in very basic algebra, the approach was always, let's see what happens if I take the natural logarithm of it, because the logarithm will take the products into sums and it will make exponentials simpler. It will make them into linear expressions. So that's the point here. We take the log likelihood function and becomes simpler, and then we take we introduce a notation. T I is the sum of all tji's for all j's, and dik is the sum over all j's of djik. Then T0 is the total waiting time in state 0 for n lives. T1 is the total waiting time in state 1 for n lives, and D01 is the total number of transitions from state 0 to state 1 by n lives, and so on. Using these definitions, the log likelihood function becomes simpler. Now, we're going to take the partial derivatives of this, set them to 0, and solve this, and we're going to get that 4 equations that you see here. And those 4 equations will give you these 4 solutions, and the estimates in each case, the maximum likelihood estimate of the transition intensity from state I to state k is the number of transitions from state I to state k divided by the total waiting time in state I. To estimate the variance of the likelihood of the maximum likelihood estimates, we first consider the second derivatives. So we would take the derivatives we had here, and we would take the second derivatives. You can see that the constant terms that don't have mu in them just drop out, and we get these 4 second derivatives. All cross derivatives, where you take derivative with respect to one parameter and another, are 0 because all the 4 equations had only one variable in them. Our first 4 derivatives, I'm sorry, not resulting equations as well, but the first 4. 4 first derivatives, that's better. Okay, the maximum likelihood estimates are independent, and for example, here is what we have, that the variance of mu x01 estimate in that hat above the mu indicates that this is an estimate. That's approximately minus the expected value of that second derivative estimate to the negative 1, and that's going to be mu x 01 squared over expected value of d01, and we take the estimate of mu x01 for that parameter, replace it there, and we take d01 to be an estimate of that expected value, and we get the estimate of the variance to be of mu 01 to be d01 over t0 squared. So just what we had before, d01 over t0 was the estimate of the parameter, and now the second derivative is very simple. The estimate of the variance resulting from the second derivative is very simple. The results for the sickness-death models are easily generalized to any Markov multiple state model, given aggregate data such that dik is the total number of observed transitions from state I directly to state k, and ti is the total waiting time in state I. Then the maximum likelihood estimate for mu xik and the approximate variance of the maximum likelihood estimate for mu xik are so the estimate for mu xik is dik over di, and the estimate of the variance is dik over ti squared. So it's a variance of the estimate. Okay? And we estimate the variance because we're calculating the variance of an estimate. The estimate itself is a random variable, and this is the approximation of its variance. Note that this doesn't say equals, it's an approximation of the variance. These values can be used to form confidence intervals based on the mean and standard deviation estimates. How? By basically taking the confidence intervals derived from the normal distribution. So it is very simplistic. It will be of the form estimate of the mean plus minus a z-value times the estimate of the standard deviation, which will be the square root of the estimate of the variance. So that's the things you need to, these are the things you need to learn about estimation at this point. I hope you enjoyed it. It's very good stuff. And I will send this video to you and then ask you to watch it. For the class on September 14th, 2023, I will also send you some other videos that I will ask you to watch. I'm basically asking you to do all the remaining exercises in the notes on multiple state models.